we shall have a look at the conformational analysis of monosubstituted cyclohexane. Now we know that cyclohexanes take up the chair conformer as its most stable form, and 99% of the cyclohexane exists in the chair form. It does undergo flipping from one chair form to another chair form, and that happens via half chair, twist boat, etc. But still, it is the chair conformer which is the most stable, and it is the chair conformer in which the cyclohexane exists. Now, when you take the monosubstituted cyclohexane, we can take the simplest example as the methyl cyclohexane. Now, we can write the methyl group in the axial orientation. Okay, so this is the chair conformer of methyl cyclohexane, wherein the methyl group is in the axial orientation. We can have it also in the equatorial orientation. Now that's possible, or we can do that by ring flipping, right? When you flip this, the axial methyl group will occupy the equatorial position. Now these two molecules, they are constitutionally the same. The molecular formula is the same, isn't it? But they are structurally different. They are called stereoisomers. Now, if they were mirror images, then we would have called them as enantiomers. But these two are not mirror images. They are, in fact, conformational isomers. Or to be more specific, we can call them as conformational diastereomers. Why do we call them as conformational diastereomers? It's because these two structures are interconvertible. They keep on changing from one diastereomer to another diastereomer. Okay, so they are conformational diastereomers. Now we need to assess the energy of these two. Now, since these are structurally different, they obviously will be energetically different too. We need to assess the energy, or we need to say if the energy is different or the energy is the same. And through that, we need to establish which is more stable. Among these two, which is more stable. Now, if you write this in a more elaborate manner, the chair conformation, you find that here, this axial methyl group, in the axial, the methyl group which is oriented axially, will be interacting with the axial hydrogen on carbon 3 and carbon 5. But similar interaction is not seen if the methyl group is oriented equatorially. Okay, it's not going to interact with the equatorial hydrogen of carbon 3 and carbon 5, or to any hydrogens on carbon 2 or carbon 6. Okay, so it's sort of this methyl group is not at all interacting with any of the groups as attached to the other carbon atoms. Okay, so the interaction is almost nil when the methyl group or the substituent is oriented equatorially. But when the methyl group is oriented axially, it is having an interaction with the axial hydrogen of carbon 3 and carbon 5. Now this interaction is called 1,3 diaxial interaction. Alright, now here you can see there are two 1,3 diaxial interactions. See, in the three-dimensional model, it's more clear. You can see the methyl groups. It is the hydrogen on the methyl group which is interacting with the hydrogen on carbon 3 and carbon 5. Now, since this methyl group is placed 3 carbon apart, we call this as 1,3 diaxial interaction. The same thing name applies for the interaction between methyl group and hydrogen on carbon 5, because if we count the other way around, this will be again 3 carbon apart. So this interaction is called 1,3 diaxial interaction, and a similar interaction is not seen in equatorial orientation, or when the methyl group is oriented equatorially. Now, because of this interaction, obviously the axial conformer will be energetic, having more energy than the equatorial conformer. Or you can say that the axial conformer will be less stable than the equatorial conformer. Now, to what extent? We need to quantify it. Now, that is very simple. We need to know what is the energy associated with the what we call the axial orientation, or associated with the 1,3-diaxial interaction. Now, the energy associated with 1,3-diaxial interaction is 0.9 kilocalories per mole. So, since there are two 1,3-diaxial interactions, there will be totally the energy associated with axial conformer will be 1.8 kilocalories per mole. So, we can say that the axial conformer is 1.8 kilocalories per mole more energetic than equatorial conformer. Or the energy of the axial conformer is 1.8 kilocalories more than the energy of the equatorial conformer. We can also just keep this in mind that the energy of the equatorial conformer is almost the same as the energy of the unsubstituted cyclohexane. This is one way of explaining the energy of the substituted cyclohexane, or that is the energy of the two different conformers or two different diastereomers, conformational isomers of substituted cyclohexane. Another way is to dissect the cyclohexane into butane units and then analyze their energy. Okay, that means the way we had divided the unsubstituted cyclohexane into butane units, 6 butane units we have seen. Similar way, we need to dissect this, or we need to we can explain the energy of the substituted cyclohexane in terms of butane units. Let us look at that. We have seen that the unsubstituted cyclohexane is associated with 6 Gauch butane units. Now, the one Gauch butane unit is formed from carbon 1, 2, 3 and 4. These 3 carbon atoms form a single butane unit. Another one is 2, 3, 4, 5. So, these 4 carbon atoms form another butane unit. Similarly, 3, 4, 5, 6, 4, 5, 6, 1, 5, 6, 1, 2 and 6, 1, 2, 3. So these are the 6 butane units which are seen in unsubstituted cyclohexane, and every butane unit is Gauch in nature, isn't it? You can see here bond 1, 2 is Gauch to bond 3, 4. Similarly, bond 1, 6 is Gauch to bond 2, 3. You see, they are the dihedral angle between these two are 60 degree. You can see here they're not entirely anti to each other. See, or neither are they parallel. They are Gauch in between. See, 1, 2 and 3, 4. Similarly, 1, 6 and 2, 3. Here you have 2, 3 and 4, 5. Okay, these two are not parallel. They are not anti either. The dihedral angle is 60 degree. So 3, 4 and 5, 6. 1, 6 and 4, 5. All. So there are altogether 6 Gauch butane units in unsubstituted cyclohexane. Now when we bring another carbon, in substituted cyclohexane, that is when we introduce a methyl group, we are introducing one more carbon atom, that is carbon 7. When that happens, extra butane units are formed. Okay, so for every carbon atom you introduce into the cyclohexane, 2 extra butane units. Apart from the 6 already present in unsubstituted cyclohexane, 2 extra butane units are introduced. So here in monosubstituted or in methyl cyclohexane, apart from these 6 butane units, we have one more, that is 7, 1, 2, 3 and 7, 1, 6, 5. these are the 2 extra butane units which has been introduced into the cyclohexane ring when a methyl group is present on the ring. Alright, so altogether now we have got 8 butane units. Now, of course, these 6, the earlier 6 are gauge in nature. Now we need to see what is the nature of the newly introduced butane units. You can see here 7-1, bond 7-1 and bond 3-2. They are again gauge to each other. They are not anti, they are not parallel. They are gauge, 60 degree. The angle between 7-1 and 3-2 is 60 degree. Similarly, 7-1 and 5-6. So they are also gauge in nature. So we can say that there are 8 gauge butane units in methyl cyclohexane when the methyl group is oriented axially. Okay, so altogether the energy of this cyclohexane will be 7.2 kilocalories per mole, because we are, the energy associated with one gauge interaction is 0.9 kilocalories. So we have got 8 similar interactions. So altogether we can put it as 7.2 kilocalories per mole. Now we can even check out the Newman projection of these 2 gauge units, or 2 conformers, newly introduced units. See, we can say that the axial methyl group is gauge to the C3 in the ring. So the axial methyl group is gauge to the C3 in the ring. So this carbon 3 and carbon 5, okay, to the carbon 7. So you can see here in the Newman projection, the methyl group is gauge to the C3. Here the methyl group is gauge to the C5. Okay, so 2 more gauge units are introduced. Alright, so altogether there will be 8 gauge units when a methyl group is introduced into cyclohexane, and if the methyl group is oriented axially. That's important. It's the axial methyl group which is introducing, or which is subtending 2 more gauge units to the ring. Okay. Now, we'll see what happens when the methyl group is oriented equatorially. So apart from the 6 gauge butane units associated with unsubstituted cyclohexane, in equatorial position also, in the equatorial conformer also, there will be 2 more gauge units, butane units. Now, which are they? They are carbon, forgot to number here carbon 7. So carbon 7, 1, 2, 3 and 7, 1, 6, 5. Now when you observe this orientation, see, carbon 7, 1 is exactly anti to carbon 2, 3, to the bond 2, 3. See, bond 7, 1. C1, C7 is anti to C2, C3. Similarly, C1, C7 is anti to C6, C5. Look at the orientation. Okay, on the first look itself, without going to the Newman projection or anything, you can easily identify the anti-subtension, or the way in which the 2 bonds are subtended. They are anti to each other. Alright, so in methyl cyclohexane, if you draw the Newman projection, it will be something like this. You can see here, the methyl group on carbon 1 is anti to the C3 methyl group, CH2. Same will be the case with C5 also. Okay, so there are altogether 6 gauge butane units and 2 anti-butane units, right? Isn't it? These 2 newly introduced butane units are anti. So, in effect, we can say that the energy associated with the conformer or with the isomer in which the methyl group is equatorially oriented will be 5.4 kilocalories per mole, because the energy associated with anti-butane unit, we are taking it as 0. That energy is taken as anti, or what we say as reference, we put it as 0, and it is with reference to that we calculate the energy of the rest of the interactions. So even though there are 8 butane units, only 6 are gauge in nature. The other two are anti in nature, and therefore we will take up only the energy of the 6 gauge units. Okay, so the energy associated with the molecule when the methyl group is equatorially oriented is 5.4 kilocalories per mole. So the energy associated with axial orientation is 7.2 kilocalories per mole, and that with equatorial orientation is 5.4 kilocalories per mole. So the difference in energy between axial and equatorial conformer is 1.8 kilocalories per mole. And that's what we have seen when we had discussed about the 1,3-diaxial interaction. The energy associated with the axial conformer is 1.8 kilocalories per mole. Okay, so in these two ways, you can explain the energy of the two isomers or two conformational isomers of the monosubstituted cyclohexane. All right. Now, here I have given a table in which the energy associated with 1,3-diaxial interaction of the compound is tabulated when the substituent varies. So the energy associated to the 1,3-diaxial interaction when the substituent is fluorine is 0.12. Okay, so it's very less than the methyl group. Okay, so since the fluorine is small, it's not going to interact much. Okay, so the 1,3-diaxial interaction will be less. Now here methyl groups comes almost 1, 2, 3, 5, fifth in position with 0.9 kilocalories per mole. See, even with that there is ring flipping happening. Okay, so with the ethyl group it is 0.95. With isopropyl it is 1.1. Now when you go to tertiary butyl group, see here the tertiary butyl group, the energy associated with it is 2.7 kilocalories per mole. Okay, one single 1,3-diaxial interaction. So similarly there will be two 1,3-diaxial interactions. Alright, so you can see that among all these listed substituents, the highest energy 1,3-diaxial interaction is shown by the tertiary butyl groups. Okay, even then comes our 1.5, that is the phenyl group. Okay, and then only comes the 1.1, that is the isopropyl group. Now when these such groups are there, such bulky groups, it's because they are bulky that they show such a huge energy associated with 1,3-diaxial interaction. Okay, see cyano group is only 0.1, the least one we can say in this list. Okay, and then comes fluorine 0.12. So they are all small molecules, small groups, so they're not going to interact much with the axial hydrogen. So when you can say that when you compare the axial conformations of the various compounds, fluorocyclohexane will be more stable than bromocyclohexane or phenol. You can say like that. I'm sorry, hydroxycyclohexane, etc. Now, coming back to the tertiary butyl group, when such a group is present, such bulky groups are present like tertiary butyl group, isopropyl group, or even phenyl group, always this molecule or this group will take up the equatorial position. Okay, and as such, any substituent present on cyclohexane will prefer the equatorial position because equatorial conformer is more stable than axial conformer. Now, this group, such a group, tertiary butyl group, will not allow the molecule to flip. If this conformer flips to the axial conformer, then automatically the energy will be very high. So such groups, the tertiary butyl group or the phenyl group or to some extent the isopropyl group, will not allow the molecule to flip. Okay, they will make the molecule to stay in this particular conformer. So these are called rigid molecules. Okay, wherein there is a bulky substituent attached. And such substituents are called anchoring groups. Okay, it will anchor the molecule to that particular conformer. The way the ship is anchored using the anchor, similarly, the molecule is anchored to the equatorial orientation or equatorial conformer by this bulky group like tertiary butyl group, phenyl group, isopropyl group, etc. Okay, so to summarize, we can say that equatorial conformer of monosubstituted cyclohexane is more stable than axial conformer, almost 1.8 kilocalories more stable than axial conformer. And the reason is because of the 1,3-diaxial interaction and also the extra 2 gauge butane units introduced to the axial conformer. Hope it's clear to you. Do write the structures and practice and make yourself thorough with the concept. Thank you.